Hello all, this is Mr. G. This is our warm-up for today's lesson, so pause the video right here, give these two problems a shot, come back when you think you have an answer. We're going over in 3, 2, 1, let's go. It says represent the domain values for which g of x is increasing and positive. Let's take a look at increasing first. Well, whenever we're doing increasing or decreasing, I like to imagine that, the function is a roller coaster. So we're in this little roller coaster car, we're going from left to right, let's see what happens. Well, we're decreasing, decreasing, decreasing. Oh, we get to there and we start increasing. So that's going to be an important point. That's when we start increasing. So that's -2. So right away, I'm going to put an open dot on -2. Let's see how the rest of the function goes. Okay, so increasing, increasing, increasing. And right there, we start decreasing. So that's another important point. What is that? X equals 5. Remember, we're talking about the x values because it's the domain values they want us to represent. And then for the rest of the function, it just decreases. So it's only increasing in between those 2 points. So we shade in between those 2 points on the number line. Now, if we wanted to represent this as an inequality, that would be, let's see, x is in between -2 and +5. So that's how we can write it as a compound and inequality. Let's take a look at number 2 next, which is where we need to represent the domain values for which the function is positive, or the g of x values are positive. So let's see, positive is above the x-axis. So this part of the function is above the x-axis. So right there, that point is going to be important. So let's see, let's circle that right now. That's a -5. Where else are we positive above the x-axis? Well, this section is above the x-axis, and we've got 2 points there. So what is that? +1 and a 9. So we've got 3 points, which is more than usual, but all we have to do is take a look at the shading we see right here and make the number line match. So from -5, we're shading to the left, so we shade to the left. And over here, we're shading between 1 and 9, so we shade between 1 and 9. To represent these as inequalities, let's see, the first one would be x is less than -4. And the second one would be x is between 1 and 9. So there we go. We represented the domain values both graphically and with an inequality. Let's take a look at the objective. Today we're doing chapter 4, section 2.5. After today, we should be able to find the average rate of change between 2 points of a function graphically. So there's 2 different ways we can find average rate of change. And in this video, we're going to talk about doing it graphically, which I personally think is the easier of the 2 methods. But let's jump in and take a look at what we're talking about here. When we talk about rate of change, hopefully this is a phrase you remember from previous math classes. All rate of change is it's just a ratio describing how 2 variables are changing. A ratio describing how 2 variables are changing. And one nice easy word that means that is just slope. Whenever we're talking about rate of change, we're really talking about slope. Now, we can represent slope in 3 different ways. We can say it's the change in y divided by the change in x. That also means rise over run. And we can also use the slope formula, which is y2 minus y1 divided by x2 minus x1. Now, the important thing to know is that these 3 things all mean exactly the same thing. They're all just different ways of representing and thinking about slope. They're different ways to get to our answer when we're talking about slope or rate of change. Let's take a look at a quick review example. So what is the rate of change of f of x? All right, we've got a line, so finding rate of change, that's just slope. We can use rise over run. To do this, we just need to pick a couple points. Let's see, this point looks good. That's right in the crosshairs, right on a whole number, x and y coordinate. And let's see, this one's pretty close to it, and it's also a good point. Now we just find the rise and run. I have to go up 1 and right 2, which means the rise is 1, the run is 2. Our slope is 1/2, and we're done. That's our rate of change for this function. But what if we had a parabola? How could we find the rate of change of this parabola? Well, let's try the same thing. Let's pick 2 points. So that point looks good, the vertex. And what's another good point? This point looks okay. That's on whole numbers. And let's find the rise over run. So that would be at 1, 2, 3, and 1, 2, 3, 4. So, okay, that means the rate of change is 3 over 4, right? No. This is not, how do I want to say this? This function g of x does not have a rate of change of 3 or 4, because if I say the entire function has a rate of change of 3 over 4, that means I need to be able to keep doing it and keep getting points. Like if I go back here, If we keep going up 1 over 2, up 1 over 2, up 1 over 2, up 1 over 2, we keep hitting points on the function. That's what rate of change means. We keep the rate of change the same, and we keep hitting the function. But let's see what happens here. We go up 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 1, 2, 3, 4. I mean, we're right away with that first point, we're off the function. So the rate of change of a parabola is not constant. Another way to say that is that the rate of change is constantly changing, which is why we get a curve instead of a nice line, a linear function. That's what makes a linear function different from other functions. With a line, the rate of change, we can do it over and over and over again. But with a curve, the rate of change is constantly changing. So we can't come up with one rate of change for this entire function. But what we can do is talk about an average rate of change. Now, the average rate of change is just the rate of change between 2 points. The rate of change between 2 points, not the whole function, just 2 points. So let's take a look at some examples of what I mean by between 2 points. So here's a graph, and all we have is 2 points. All right? It's not a complete continuous function, but we can find the average rate of change between these 2 points by using rise over run. Let's see. So we go up 1, 2, 3, 4, 5. So that's up 5, and 1, 2, 3, 4, 5, 6, 7, 8, 9 to the right, which means these 2 points have an average rate of change of 5 over 9. Now, I want to look at a few more pictures to hopefully solidify that the average rate of change is just between 2 points. So let's say we had a quadratic now. Now, I'm going to go back and forth between these 2 slides. Don't look at the function, just look at the points. Are those points changing? No, the points are exactly the same, which means the average rate of change will still be 5 over 9. I don't care that there's a curve in between the 2 points now. The average rate of change does not change between those 2 points. What if it was something like this? Or here we've got, that's definitely not a quadratic. I guess it's like a sine or a cosine function. Maybe we haven't even seen those before, but we don't care what the function looks like. Let's just take a look back and forth. Did the points change? The points are exactly the same. So even though, we've got all this crazy stuff going on in between the points, the average rate of change is still 5 over 9. One more. Now this function looks completely insane. I don't think we've seen one like this before in this course, but I mean, it's not connected at all. We've got one arrow going down, one arrow going up. What's going on here? But we don't care right now because we're only focused on the average rate of change. So just look at those 2 points. Don't look at the functions. Look at the 2 points. Those 2 points change? Nope. So the average rate of change is 5 over 9. Even though the function is not even connecting these 2 points, we can still say the average rate of change is 5 over 9 because we don't care about the function. We only care about the 2 points, our starting point and our ending point. All right, let's take a look at some examples now. Example 1 says, find the average rate of change of the function f of x between x equals -4 and x equals 2. All right, so to use the, how do I want to say this? What the function tells us here, what the graph tells us is what our starting point and ending point is. So first let's go to x equals -4. So x equals -4 is right here. So that hits our function right there. So that's the starting point. And x equals 2 hits the function right there. That's where the function is at x equals 2. Now all we need to do is do rise over run. Do our slope, the average rate of change between those 2 points. So I'm going to go up 1, 2, 3, 4, 5, 6, 7, 8. To the right, 1, 2, 3, 4, 5, 6. So rise over run, that would be 8 over 6. But we can simplify that. Let's divide both of them by 2 and make it 4/3. And that's our average rate of change between those 2 points. Take a look at example 2. Here it says find the average rate of change of the function f of x between x equals 2 and x equals 8. So they're just giving us 2 new points, 2 and 8 for x value. So let's find our starting and ending points. There's x equals 2, that hits the function right here. X equals 8 hits the function right here. Now we do our rise over run. Well, we don't go up or down at all, so our rise is 0, and the run is 1, 2, 3, 4, 5, 6. But I mean, let's be honest, the run doesn't actually matter. As soon as we get a rise of 0, no matter what number's in the denominator, 0 divided by anything is 0. I guess the one exception there is 0 divided by 0 is undefined. But if it's 0 divided by anything besides 0, then it's just going to be 0. And we're done. That's our average rate of change between those 2 points on this function. Now this one I want you to try it on your own. I'm going to scroll down a little bit so you can more easily see the graph. I want you to find the average rate of change of this function f of x from x equals 5 to x equals 8. So go, try this on your own. Come back when you have an answer. 3, 2, 1, let's go. X equals 5 is our starting point. That hits the function right here, right at the vertex. And x equals 8 is our ending point. It's right there. Now we do rise over run. We go down 1 this time, so it's negative 1 and 1, 2, 3 to the right. So it's just negative 1 over 3. No need to simplify because that's already as simple as it can be. Let's write that a little bit better though. Negative 1/3, there's our average rate of change. All right, at this point, you might be tempted to stop the video and say, man, I got this. I don't need to watch the rest of this. But these last two examples we're going to do are not throwaway examples. So stay with me here. We want to find the average rate of change of the function g of x between x equals negative 3 and x equals 1. Now, if you're looking at this and you're trying to think, okay, well, I'm sure Mr. G has a reason for doing two more examples. So what's different here? Some students might say, okay, well, yeah, I mean, here we've got sort of more of an angular function. It sort of looks like a bunch of linear functions connected, sort of a piecewise function, if you've heard that phrase before. But that's not why I wanted to do this. I mean, that makes it a little bit different, but remember, the function only gives us the starting point and the ending point. What's different about this example is right there on the y-axis. The increments we're going up on the y-axis are different than the increments on the x-axis. So let's look at the x-axis. That's just 1, 2, 3, 4, 5, 6. It's just going up by increments of 1. But on the y-axis, it's going up by 0.25, 0.25, 0.5, 0.75, 1, which means we have to keep that in mind when we're finding our rise over run. So let's take a look at this problem now that we've sort of set it up. So x equals negative 3 is right here. Hits the function right there. X equals 1 there. Hits the function right at the top. Now we find our rise over run. But remember, we have to be careful when we're counting because the y units are going up by 0.25. So let's count carefully. 0.25, 0.5, 0.75, 1, 1.25, 1.5. So that's going up 1.5 since we're going up by increments of a quarter. And then the x values are just going up by increments of 1. So it's 1, 2, 3, 4. Now we just write it as rise over 1. 1.5 over 4. I don't like having that decimal in the fraction, so to get rid of that, I'm going to double this. Because if I double 1.5, we get 3, and double the denominator, and we get 8. I think that's a much nicer way to have our answer written, 3/8. Just one more to go, and I want you to try it on your own. So let me scroll this down so you can see the picture a little bit easier, get my face out of the way. So I want you to find the average rate of change between x equals negative 1 and x equals 9 for this function. 3, 2, 1, let's go over it together. X equals negative 1 is right here, that point on the function. X equals 9 gets us there on the function. Now it's time for rise over run, but we have to be careful as we count. So it's 0.25, 0.5, so that's negative 0.5 for the rise because we went down. Then the x is just 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then we do our rise over run, which is negative 0.5 over 10. I'm going to double this again, or multiply both the numerator and denominator by 2, I should say. And we get negative 1 over 20. And that's our average rate of change between these 2 points, between those two x values. Hopefully that's the answer you got. Let's take a look at our assignment for today. So I want you to do worksheet 4-2.5, numbers 4 through 10. Now, in case anyone doesn't have the worksheet, I'm going to quickly scroll down, or rather slowly scroll down, so you can just sort of pause the video where you need to take a look at these problems and give them your best shot. Yeah, hopefully that was slowly enough so you can see them all. If you have any questions, as always, let me know. Enjoy the rest of your day.